Hi again. We're gonna continue with chapter 7 now. We finished with 7.2. We're gonna skip 7.3 and move on to 7.4. Here we're kind of continuing with what we looked at in 7.4. We looked at expectation of a function of two random variables. So here let's look at something special that happens in a particular case, okay? So we have proposition 4.1. What does that say? If x and y are independent random variables, and h and g are some functions, then what if you're looking at the expectation of this kind of a function of x and y? So the function that you have is a product of a function of x and a function of y. So in this case, what will be the expectation? This turns out to be just the expectation of the function of x, g of x, times the expectation of the function of y. Okay? So let's see how that goes. So you have x and y are independent. So let's suppose that we'll do the continuous case. Okay, suppose that x and y are jointly continuous with probability density function f of x, y. Okay, then you know, since x and y are independent, you have that this f of x, y is equal to what? It will be the product of the density of the random variable x and the probability density function of the random variable y. Okay? All right. So, going back to the formula we got in 7.2, what is the expectation of g of x times h of y? You know, we'll use you can think of what we had before. We call this, we had a function of x and y that wasn't necessarily a product. What formula did we have? The expectation is the double integral. You can write minus infinity to infinity or to whichever you want of the function times the joint density. However, we'll apply that this is equal to f sub x times f sub y. And just using the properties of integrals, you know, these are functions, not functions of x, they're functions of y. You can pull these out of the inside integral, and then what you have inside is integral g of x times f sub x dx. That's a constant as far as the integral dy is concerned, so you can completely pull that out. So this whole thing, just like you did in Calc 3, you can rewrite as an integral of g of x times f sub x and integral of h of y times f sub y of y. Okay, well, what do you know? What is this? This is this is the density of x. Here's a function of x. This is the expected value of g of x. And what is this? This is the expected value of h of y. So there you go. If x and y are independent, and the function is a product of a function of x times and a function of y, then the expectation of that product is the product of the expectations. Okay, so you have to be careful. You need that x and y are independent to have this happen. Okay. All right. So this is the proof for the continuous case. In the discrete case, you have the same thing. You have a double sum. You can write down the probability mass function as a product of the probability mass functions and take one out of the inside summation and so on and prove exactly the same result. Okay? All right. So let's move on to a big definition, and that is of the covariance. Okay, the covariance of two random variables is playing the role of what the variance did in the single variable case. Okay, so the covariance between random variables x and y, it's denoted by COVX comma y and defined by the covariance is the expected value of x minus its expectation times y minus its expectation. Okay, so just remember, what did we have in the variance case? You remember what was the variance of x? The variance of x was the expected value of x minus its expectation squared. Okay, so this is similar. Instead of a square here, you have this product. Okay, so just an aside, I was just trying to draw the analogy between the two. All right, so that's the definition of covariance. Okay, and just like you had with the variance, you could rewrite it in a certain way using the definition. Once you open up the square and write it down, you had that this was the expectation of x squared minus the expectation of x whole squared. We can do something similar over here, and let's work that out. Okay, so let's see. So we have that the covariance of x and y is the expectation of x minus e of x times y minus e of y. Okay, and let's open that up. You have x times y minus x times e of y minus y times e of x plus e of x times e of y. Correct? So all I did was just took the product inside the square brackets. Okay, so now you have expectation of some of these things. Let's write it down as a sum of the expectations and take out these constants. Then I will have this. Okay, so let's look at these individual things. What do you have here? E of y is a constant, so you can take it out. E of x is a constant, so you can take it out. E of x times E of y, that's just a constant. The expectation of a constant is just the constant. So we can rewrite this as E of xy. I've taken out the E of y, so then I have E of y times E of x. I've taken out the E of x, I have E of x times E of y. And this is expectation of constant, that's just the constant, so it's E of x times E of y. Well, you see, all these are the same. It's just the product of the expectation of x and the expectation of y. So just combining these terms, two of them are with the negative, one with the positive. So you have E of xy minus E of x times E of y. Okay? So you see over here, this is the analogous result for covariance, analogous representation for covariance that you had for variance with the squares. And in fact, if you take y to be equal to x, what do you get? You get covariance of x and x will be what? It is expectation of x times y, or x times x, it's x squared, minus expectation of x times expectation of x squared. So this is in fact the variance of x. That is one of the results that you have. The covariance of x times x is the variance of x. Okay? And of course, if you look at the covariance of x, y, just by basic formula, you can see that's going to be exactly the same as the covariance of, covariance of yx. And I will let you prove this. What about the covariance of ax times y? So everywhere you see an x in over here, I mean, you don't have to use that. You can just use the formula. This will be the expectation of ax times y minus the expectation of ax times the expectation of y. Just working it out, you know, this will just going to be a times the covariance of x times y. Okay? So you have that. And in fact, these are the results in proposition. Actually, let's write that. This is proposition 4.2. Okay, this is number 2. This is number 1, and this is number 3. Okay, and now let's look at the most involved of this, the parts from proposition 4.2, and that is the covariance of a sum I equals 1 to n. Let's make that look more like an I equals 1 to n of xi's. And if you have a sum of yj's, j equals 1 to m. Okay, what will this turn out to be? This turns out to be the sum of the individual cross xi, yj terms, double sum over I and sum over j. Okay, so the proofs of parts 1, 2, and 3 we just discussed, and you could easily do it. Let's do the proof for this last part. Okay, all right. So think about it. What will you have? You have that you want to look at the covariance of the sum of the xi's and the sum of the yj's. Okay, we're going to be using this term a lot. So what we're going to use is some shorthand notation for the expectation of xi and the expectation of yj's. Okay, so let mu I be the expectation, oops, let me just make this smaller, of xi, and let nu j be the expectation of yj. All right, okay, so then let's just use certain things. Then what if you wanted to look at the expectation of the sum of the xi's? Then you know this will just be the sum of the expectations. So this will just be the sum of the mu i's. Similarly, expectation of sum of the yj's. This will just be the sum of the nu j's. Okay. And now let's write down what the covariance turns out to be and expand it. All right, so the covariance of sum of xi and the sum of yj's, what is this? This is, by definition, the expected value of the sum of I equals 1 to n of xi's minus sum of I equals 1 to n of mu i's times, actually, let me write it smaller. Sorry. Okay, so what did I use over here? I just used the definition. Okay, and I use that over here. You have expectation of the sum is the sum of expectations. All right, so normally what would I have? The expectation of the sum over here of the x's, and over here I would have expectation of the sum of the y's, and they just turn out to be this just by these. Okay, all right, so what do? Let's open this up and take a product. Oops. To make it simpler, we're going to combine these two. So each individual one I will subtract from the individual. So you have summation, the sum of these xi's minus the sum of the mu i's, so you'll have x1 plus x2 blah 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 plus xn minus mu1 minus mu2 blah blah blah. So I'm going to do this minus this plus this minus this, just rewrite it like this sum. Okay, that's the first term, and the second one in the same way, j equals 1 to m, I'm going to rewrite it as yj minus nu j. Okay, exactly in the same way, combining the terms with the same subscripts together. Okay, so now I have this product, and I'm going to think of this as this sum of these terms multiplied with the sum of these terms. So leave them together as one and take a product, and what you're going to get? You're going to get a double sum of xi minus mu I times yj minus nu j. Correct? Okay. And now what? Let's take the product inside over here. And what will you have when you take the products inside? Actually, sorry, let's not take the product inside yet. All we want to show is we want to get the covariance of xi, yj. So that's in fact what we have right here. So what do we need to do? We want to show the covariance of sum of xj's and sum of yj's is the sum of the covariances. So what do we want? We want to show that this is the sum. So we want to bring the sum out. And you have an expectation of a sum of many terms. This is just a double sum. That's just a sum of many terms. Expectation of sum is sum of expectation. So we can in fact pull that out right now. And you have this. Okay, but what is this? You can see this is exactly the covariance of xi and yj. So you have that the sum of covariance of sum is the sum of covariances. Okay, so it's just like, in a way, you can see that really there's not much deep stuff going on. You have covariances. First, you're writing the xi minus the expectation together. You're thinking of it as expectation of x minus mu, putting it together, rewriting the product as a double sum of products, and then taking the expectation in. Okay, so that's all we've done. And you can just apply this. If you have the covariance of summation xi and summation xi, then you know that that's just the variance. So for example, if you have the variance of the summation of xi's, that is just the, like we've seen, that is just the covariance of the summation xi with the summation xi. Okay, and we have seen what that is just the double sum of the covariances, but we don't need double sum over here. I mean, yeah, that's just the double sum of the covariances, sorry. And let's use a different letter here, J. Okay, even though it's the same thing, just so that we can keep track of which one we're talking about. Okay, and this will be the covariance of xi, xj. All right, and what do we have over here? We're doing a double sum of covariance xi, xj. So think about it. What are you having? You'll have x1, 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 x2, blah, 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 all the way till x1, xn. Then you'll have x2, x1, x2, x2, blah, 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 all the way till x2, xn, and so on. So that's what will be there in this double sum. That's why we're calling it a double sum. When you write it down as a table, it's most natural to write it down as this two-dimensional thing. Okay, so what can we do? Let's split the xi's, covariance of xi separate from when the subscripts don't match. So we will write it as sum when they do match. Okay, plus the sum when they don't match. Okay, so what am I saying? If you look at this sum, you're going to rewrite it as separately all this x1, x1, x2, x2, all the way till xn, xn. And then the rest of it, you're writing it as a double sum I naught equal to j. Okay, now when you look at I naught equal to j, what can you do with this? You can think of this as, when you look at this grid, you have x2, x1 here and x1, x2 over here. So since you have covariance of xi, xj equal to the covariance of xj, xi, instead of having terms repeat, you can just look at, the terms above this diagonal or the terms below this diagonal, however you want to look at it, not deal with both of them, and just have a double sum of I less than j, but then you have to multiply it by 2 because what's above the diagonal is equal to what's below the diagonal when you take covariance of each one of them and add it. And so if you're just considering one of them, you'll have to double this and you'll have a covariance of xi, xj. Okay, and what can we do now? So this you will rewrite again. What is this? This is just the variance of xi's, and so sum one going I going from 1 to n of the variance plus 2 times sum I less than j of the covariance. Okay, so that's what you have as a formula for the variance of a sum. The variance of a sum is the sum of the variances plus the covariance of terms when they're unequal, or if you just keep a strict order, you'll always have I less than j, then it'll be twice that. Okay, whichever way you want to look at it, it's fine. If you don't want to do it like that, then you could also alternately just write summation I not equal to j, covariance of xi, xj. Okay, whichever way. Okay, but I mean, in this picture, you kind of understand, I hope. Not kind of, you understand, I hope, what I mean when you could just put a 2 if you're not going to include all of the terms. Okay? All right, so that's what we have as a result for our variance of sum. And I'm just going to write it down as a formula here. Okay. All right. And when you look at these xi's, if the xi's are independent, pairwise independent, so if x1 is independent of x3, x1 is independent of x2, x1 is independent of all the others, x2 is independent of x1, x3, x4, x3 is independent of x1, 2, x4, x5, and so on. If they're all the xi not equal to xj are independent pairwise, then what can you have? Then you have that the covariance is 0. So that's something else you can write. So if the x1, x2, blah, 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 xn are pairwise independent, then since covariance of xi, xj when I not equal to j will be 0, since independence, okay, so then this covariance will be equal to 0 since independence implies covariance is 0. Then what do you have? If they're pairwise independent, then and the above formula becomes variance of a sum is the sum of variances. Okay, so I hope that you don't always have that the variance of sum is sum of variances. You do need that the covariances are 0. And if you have independence, then you automatically have that the covariance is 0. Okay, why? Because if you have independence, let's just see 1 second. Let me step back a second and prove it. So if x and y are independent, sorry, I should have mentioned this before, then covariance of x, y is 0. Why? You can actually prove it easily. Okay, what is the covariance of x, y? The modified formula said that's the expectation of x times y minus the expectation of x times the expectation of y. But you know if x and y are independent, what is this? This is the expectation of x times the expectation of y, right? We saw this. This is the proposition we just saw above. If x and y are independent, then the expectation of g of x times h of y is the expectation of g of x times h of y. So take g and h both to be the identity functions. So it's expectation of x times y. And just applying that over here, you have that the covariance, which is expectation of x times y minus expectation of x times expectation of y. This turns out to be this, and this stays the same. So you do have that they cancel and you get 0. Okay, so if x and y are independent, then the covariance is 0. So you should remember that. Okay, and here's a little proof of that neat, cute, small little thing. How about the other way? If covariance is 0, can you conclude that x and y are independent? Let's take a tiny little example and see that actually that turns out to not be true. Okay, so let's see. Okay, well, let's take a look. So we're going to create 2 random variables. So let's suppose you have the random variable x is got range of just 0, 1, and -1. So let's say the probability of x equals 0 is 1/3, and that's the same as the probability of x equals 1, which is the same as the probability of x equals -1. So x is 0, 1, or -1 with equal likelihood. It's a discrete random variable. And now let's create the random variable y. and we'll define it in this way and define y to be 0 if x is not equal to 0, and you define y to be 1 if x equals 0. Okay, so clearly the random variable y depends on x, and in this case what you have is x times y. Firstly, x can be 0, 1, or -1. When x is 0, y is 1. When x is 1 or -1, y is 0. So this product is always 0. So then the random variable x times y is a constant, and this constant is 0. It's not really random now, it's a constant 0, but that's okay. And we have that the expected value clearly also is 0. Okay, how about the expected value of x? Well, that's easy to calculate. It'll be 0 times 1/3 plus 1 times 1/3 plus -1 times 1/3. And this will just be 0. 0 plus 1/3 minus 1/3. So you have that 0. So what about the covariance of x and y? Well, that's the expectation of x times y minus the expectation of x times the expectation of y. You can always use this formula if you prefer. And you have that this is 0 minus 0, so that's 0. Okay, so here are two random variables where the covariance turned out to be 0, but clearly y depends on x. So, but clearly you have that x and y are not independent. Okay, so there you go. You should remember this. If covariance is 0, does not imply independence. However, if you do have independence, then you certainly do have that the covariance is 0. All right, and we'll do one example now involving the sample mean. If you do any kind of statistics by sampling, you will see this. Okay, maybe you've already seen it. Okay, so let's take a look at that. That's example 4a, and that's all that we'll do in this section. We're not going to do anything more then. Okay. Okay, so let me write down the details. You have that x1, x2, blah, 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 xn. Let x1 through xn be independent and identically distributed. What does it mean? All of them have the same distribution. They're all normal random variables with the same mean and same variance, or all of them are binomial with the same n and same p, or all of them are Poisson, or all of them are exponential, or all of them are uniform on the same interval, everything. Okay, so they're all the same distribution. Okay, so let x1 through xn be independent and identically distributed. Okay, but that doesn't mean they're the same. So if I roll a fair die and xi is the value that comes up on it, and you roll a fair die, or x1 is the value that comes up on it, and you roll a fair die, x2 is the value that comes up on it, x1 and x2 are independent and identically distributed, but they're not the same value. Okay, so just be clear that just because something's independent, identically distributed, it doesn't mean that, just because something's identically distributed doesn't mean it's the same random variable. Of course not. Okay, so let x1 through xn be independent and identically distributed. Random variables with the same, with mean, mu, or actually let me write expected value. Mu and variance sigma squared. Okay, and you will let x bar be summation xi over n. All right, Oops, sorry. Okay, so that's called the mean. Then you have these quantities xi minus x bar for I going from 1 through n. They are called the deviations. As they tell you how far xi is from the mean, okay? From this is called the sample mean, from the sample mean. They're called deviations. They tell you how far the individual data points are from the sample mean. All right, and then the random variable s squared, which will be the sum of xi minus x bar squared. So what are you doing? You're looking at xi, you're subtracting the sample mean. This is also a random variable, don't forget, okay? Because this will depend on all the different xi's. You're going to add it up and divide by n. Okay, this is not the expected value of xi. This is the sum over n. This over n minus 1. I going from 1 to n. This new random variable that we create is called the sample variance. Okay, so this one is called the sample mean. This is called the sample variance. Okay, you've seen that. This is called the sample variance. What you want to calculate is find A, the variance of x bar, and B, the expected value of, so find the variance of the sample mean and find the expected value of the sample variance. Okay, so looking at this, what is one very natural question that you have? I'm guessing that you stared at this and wondered, why do we have an n minus 1 instead of an n? You would think that, you adding all these n deviations and squaring them, you squaring all the n deviations and adding them up, you should divide it by n, not n minus 1. And that we will see when we calculate the expected value. You will see why. Okay, so let's take a look at this. Let's find these. Okay. So what is the variance of x bar? The variance of x bar will be the variance of this sum, right? Okay. This 1 over n is in every single term in the sum, so I can take it out like this. And when you have a constant inside a variance, you can take it out, but it'll come out with a square. Okay, so you have that the variance of x bar is 1 over n squared times the variance of a sum. But what do you know? These xi's are independent. So what did we just look at? The variance of a sum is the sum of the variances. Okay, and you know that variances, each one of them is sigma squared. You're adding up n of them, so it's n times sigma squared over n squared. So you'll have sigma squared over n. Okay, so the variance of x bar is 1 over n times the variance of x. All right, so don't forget these xi's all have the same variance, sigma squared. Okay, And now let's look at part B and let's find the expected value of s squared. Okay. Okay, so what is s squared? S squared is the summation of xi minus x bar whole squared over n minus 1. Instead of looking at expectation of s squared and have this n minus 1 floating around over there, what we're going to look at is just n minus 1 times the expectation of s squared, okay? Then we don't have to fidget with the 1 over n minus 1 in each term. Okay. All right, so we look for this. Okay, so n minus 1 times the expectation of s squared. What will that be? Oops, sorry. Okay, so first let's look at the term without the expectation. N minus 1 times s squared. What is it? It is n minus 1 times sum I going from 1 through n of xi minus x bar whole squared. Okay, all right. So what we're going to write down, oops, sorry, there's an n minus 1 here. Okay, and that's why we didn't want to deal with that. So this is just sum I going from 1 to n. You can pull that n minus 1 out of the summation. And it'll cancel with this. So xi minus x bar squared. Okay, so what we're going to do inside the square is a little trick. We will subtract mu and add a mu. Okay, so I just subtract and add. So I just essentially just added 0 over there. Okay, and then I'm going to think of these terms separately. xi minus mu. Okay, and then minus, I can say x bar minus mu whole squared. All right, so let's write down what this square is going to be. Okay, it will be sum I going from 1 to n xi minus mu squared minus 2 xi minus mu times x bar minus mu, okay, plus x bar minus mu whole squared. All right, just rewrite this, split up this summation, and what do you have? Summation I going from 1 to n xi, I'm sorry, some of my i's look like j's, xi minus mu whole squared minus, now when I put the summation to this term, what do you know? This x bar minus mu has got nothing to do with I. Okay, it doesn't have a subscript I in it. So you can pull it out of the summation and just have a sum with the xi minus mu. All right, and when you add up summation of x bar minus mu squared, oh, let's just write it down. Summation I going from 1 to n x bar minus mu whole squared. Well, once again, like I said, this is a constant as far as the summations go. Actually, this is not a constant. What I mean to say, this doesn't have any subscript in it. So it doesn't change with each I. So you can take it out of the summation and just sum up 1. So you'll have an n over there, okay? So just putting this down all very nicely. You have xi minus mu squared minus 2 times x bar minus mu, summation I going from 1 to n xi minus mu. And then you're adding up this term n times. If you want, you can think of it like that. So you'll have n times x bar minus mu whole squared. Okay? All right. Now, take a look at this. You have summation of xi minus mu. Let's just, the center term. So we can think of this as summation I going from 1 to n of xi minus summation I going from 1 to n of mu. Okay? And what do you have as summation I going from 1 to n of xi? Look at x bar. X bar is summation I going from 1 to n of xi over n. If you multiply both sides by n and pull this n out, this is exactly n times x bar, right? And this is exactly n times mu. Okay, so I can write this as n times x bar minus mu. Okay, so I'm not writing every single step again, it's just this part that I put a squiggly line under. So the whole thing I will rewrite as I going from 1 to n, xi minus mu squared minus 2 times this product. Okay, so you have x bar minus mu over here. So you'll have minus 2n times x bar minus mu squared plus n times x bar minus mu squared. Oh, okay. So you know that is just summation I going from 1 to n of xi minus mu squared minus n times x bar minus mu squared. All right. And what was this? If you remember, this is n minus 1 times s squared. So all we've done so far over here, actually, let's just erase this to make it looking nicer. All we've done over here is we have just done some algebra, applied the definition of x bar in there, and come up with the form that n minus 1 s squared is exactly this. All right. And now let's take expectations. Okay, so n minus 1 is a constant that'll come out of the expected value on both sides. Okay, I should write. Okay, and here you'll have expectation of a sum in the second term. That's just the sum of the expectations. We've seen that. All right. And over here you have expected value of x bar minus mu squared. Okay, let's put a parentheses like this. All right. Okay, well, what is this? This, is sigma squared. That is just exactly the variance of xi. Okay, you're adding up n of them, so this is n times sigma squared. All right. And then what is this? This is, if you know, mu is expectation of x bar. So this is exactly the variance of x bar. So you have minus n times variance of x bar. Okay. Why is this the expectation of x bar? That's we've calculated that before, but that's easy to see. You have expectation of some xi over n. Take this out, so you have 1 over n, and you can take the summation of the expected value. They are identically distributed, so they're all of them mu, so it'll be 1 over n times n mu, so it'll be mu. All right, just as an aside. Okay, so now you have n sigma squared minus n times the variance of x bar. We just calculated what the variance of x bar is, and that was sigma squared over n. So let's plug that in here. And what does this turn out to be? This turns out to be n minus 1 times sigma squared. Okay, So you have the result that n minus 1 times the expectation of s squared is n minus 1 times sigma squared. So the expectation of s squared is exactly sigma squared. And that is why in the definition of s squared you needed a 1 over n minus 1. If you had a 1 over n instead of a 1 over n minus 1, then what would have happened? There would have been an n over here, and you'd have n minus 1 over n in front of the sigma squared on the right. You wouldn't want that. You want that the sample variance has the exact same variance as the original sample, okay, or as the original x size. All right, so you would see this a lot as the sample variance and the sample mean. You see it a lot when you're looking at data and trying to figure out how the data is distributed and so on. Okay. All right, so that brings us to the end of 7.4. We're not going to look at any more of 7.4 now, okay? Next section would be conditional expectation, but for now, we're done with this, okay? All right, I hope that made sense, and not just this, even the previous videos, and that the semester is going all right for you guys, okay? Please feel free to email if you have any questions whatsoever. Okay. Good luck, guys.